Look at organic chemistry, and we're specifically going to look at carboxylic acids and esters. So our learning intention is to explore the structure, nomenclature and properties of planar carbons, and we're going to focus on carboxylic acids and esters, as I've already mentioned. So we're going to look at planar carbon compounds in this video, and from our slide here you can see that there's 4 planar carbon compounds. There's aldehydes, ketones, carboxylic acids and esters. We've already addressed aldehydes and ketones in another video, so in this video we're going to look at carboxylic acids and esters. So the first thing to always look at is to look at the functional group of a compound. So carboxylic acids have a functional group of COOH, and that has this structure here. So our carbon is here, so C double bond O, and then there's an OH at the end. So for a carboxylic acid, again, similar to the aldehyde, the carboxylic acid functional group will always be found on the end of a structural diagram. So that's important to look out for. Also, the general formula is CnH2n plus 1 COOH, where COOH is your functional group and CnH2n plus 1 is your alkyl chain, and N is the number of carbons in your chain. So naming carboxylic acids, it's very similar to the naming process that we would have had for aldehydes and ketones. So you identify the longest continuous chain of carbon atoms. You change the ending from E to oic acid. So that simply means that you remove the E and you add oic acid instead. You number your carbon chain such that the COOH has the lowest possible number, and then you indicate the position of any substituents that are present, and you then go and form your name. So here's some simple carboxylic acids. So first one here is methanoic acid. So we know that methanoic acid means 1 carbon. So this is our methanoic acid structure here. And that's further confirmed by our HCOOH. Next is ethanoic acid, so eth is 2 carbons, so that matches up with this structure here. Propanoic acid is 3, and butanoic acid is 4. And as you can see in each of our chemical formulae, you can see that we have the COOH on the end of all of them, and attached to the COOH then is either a H or a CH3. So that is, the blue part is the non-polar part of your carboxylic acid, and the yellow part is the polar part. So let's try an example here. So step 1 is always to identify your longest carbon chain. And I can see here 1, 2, 3. So my longest carbon chain has 3 carbons in it. So I know that that is prop. So that would be propane, but I know for a carboxylic acid that I remove the E, and what it becomes is propanoic acid. So that is step 1 and step 2 completed. Step 3 tells us to number our carbon chain such that our functional group has the lowest possible number. So we do that, 1, 2, 3, and then we indicate any substituents. So I can see that I have a 3 bromo and I have a 2 chloro. Then we just need to assemble the name in step 5. So you assemble alphabetically. So it will be 3 bromo, 2 chloro, propanoic acid. And it's important here that you remember that you assemble your substituents alphabetically and not numerically. So some physical properties. Methanoic acid and ethanoic acid are liquids at room temperature, while propanoic acid and butanoic acid are solids. Short-chain carboxylic acids are soluble in water due to the polar COOH group, which gives them the ability to form hydrogen bonds with the water. As the carboxylic acid chain gets longer, its solubility in water decreases, so longer chained carboxylic acids are more soluble in non-polar solvents such as cyclohexane, because the non-polar part of the carboxylic acid is getting bigger. So if we look at boiling points of carboxylic acids have higher boiling points than corresponding alcohols. And this is because carboxylic acids can form something called dimers. And dimers are where two carboxylic acid molecules are held together by two hydrogen bonds. And you can see this down here, a dimer, where we have a carboxylic acid where two of them are been held together by hydrogen bonds between the OH of one carboxylic acid and the C double bond O of another. And that's what this last point says. It says this is possible due to the polarity of both the C double bond O and the OH bonds in each of the carboxylic acid molecules. So, uses and occurrence of carboxylic acids. So, methanoic acid is actually found in the sting of ants and nettles. So, if you get a nettle sting, it's actually methanoic acid that is causing the sting. Ethanoic acid is the main acid in vinegar, and you should remember that from your titrations of finding the amount of ethanoic acid present in vinegar. Ethanoic acid is also used in the manufacture of cellulose acetate. Now, cellulose acetate is it used to be used in films for photography, but in more recent times it's actually used as a synthetic fibre, and it coats playing cards. So that shiny coating that's on playing cards in a deck of cards is cellulose acetate. Propanoic acid and benzoic acid and their salts then are used as food preservatives as well. So the last of our planar groups to look at is the esters, and esters are formed by the reaction of a carboxylic acid and an alcohol. And esters have this functional group here on the top right hand corner. So as you can see, it's C double bond O O, and on either end then here you will have an alkyl chain. So if we take a look here, we said it's formed by the reaction of a carboxylic acid and an alcohol. So if we look here, we can see we're reacting ethanoic acid and methanol. And basically what we have is we have the CH3 and the COO of our ethanoic acid and the alkyl part of our alcohol reacting together to form your ester. And the other product of that reaction will always be water. So basically what you need to do is, if you're ever asked to form an ester, remove the OH from the alcohol, remove a H from your carboxylic acid to form your water, and put what is remaining together to form your ester. Now, this is called an esterification reaction, and an esterification reaction is an example of a condensation reaction. So we're going to define a condensation reaction, and a condensation reaction is a reaction in which two molecules combine to form a larger molecule with the loss of a smaller molecule, such as water. So when naming an ester, the best thing to do is always draw down the structure, but divide it into the parts derived from the carboxylic acid and the parts derived from the alcohol. The first part of the ester name will always come from your alcohol, with the anol ending changed to YL. So for example, ethanol will turn into ethyl, and the second part of the name then comes from the carboxylic acid, where you change the oic acid to OH. So in methanoic acid, the oic acid disappears and you end up with methanoate. So let's try an example of naming an ester. So step 1 is to divide your ester into the part derived from the alcohol and the part derived from your carboxylic acid. So here in the yellow, that is the part derived from the carboxylic acid, and the part here in blue is the part derived from the alcohol. So I can clearly see that the alcohol was methanol, but I know that we remove the anol and add "-ile", so it's methyl. And I can clearly see that the carboxylic acid was methanoic acid, and I know that because there is one carbon in the carbon chain. So we get rid of the oic acid and we add O8 on the end. So that means that this structure here is methyl methanoate. So that is the name of this carboxylic acid here. So alcohol and the part derived from the carboxylic acid. So this yellow piece here is the part that is derived from the carboxylic acid, and the blue part here then is the part derived from the alcohol. So if we start with the alcohol, I can see that there's 2 carbons in the chain of my alcohol. So that means I would have been dealing with ethanol, but I know that the anol comes off and it becomes ethyl. Now, if we look at the carbon chain in our carboxylic acid, I can see that there is 2 carbons in my carbon chain for my alcohol, so I would have been working with ethanoic acid there. But I know then that the oic acid disappears and this becomes ethanoate. So that leaves me with an ester name of ethyl ethanoate. When it comes to esters, you'll only ever be asked up to C4, and here is the list of all the possible ester names that can be involved with carbons up to C4. If we look at physical properties of esters, all esters are liquids at room temperature, and they have low boiling points due to their inability to undergo hydrogen bonding with each other. Most esters have a smell, and it's usually a sweet smell. So esters are soluble in water and non-polar solvents such as cyclohexane. However, as the number of carbon atoms in an ester increases, solubility in water decreases and the solubility in the cyclohexane increases. And that's because the non-polar part of your ester would be getting bigger. So the last thing to look at then is the occurrence and uses of esters. So esters occur naturally in fruits, and they're responsible for their flavours, and they occur naturally in flowers, and they're responsible for their pleasant smells. Fats and oils are naturally occurring esters, and that's due to the long-chain carboxylic acids that are present. And ethyl ethanoate is a solvent that is used in printing inks and paints. That's it for this video. Have a read over the learning intention to make sure you understand everything we've gone through.